quotient rule. As the product rule applies when we have to take the derivative of a product of two functions, the quotient rule applies when we need to take the derivative of a quotient of two functions. The quotient rule can be written as follows. If you want to take the derivative of a over b, we're going to take a prime b minus b prime a all over b squared. Verbally, we think of this as the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Example 1 here, we want to find the derivative of g of x, which is x plus 3 over x squared minus 4. Well, when I take the derivative, the first thing we're going to do is write out the quotient rule. We're going to take the derivative of the top, multiply it by the bottom, which is x squared minus 4, minus the derivative of the bottom, which is x squared minus 4, multiplied by the top, all over the bottom, which is x squared minus 4, squared. So if we do the derivative of x plus 3, we just get 1. Do the derivative of x squared minus 4, we get 2x. And here we're going to divide by x squared minus 4 squared. The quotient rule is fairly long and complicated, and using it is not always the best way to differentiate a quotient. If the denominator in the quotient is simply a power of x, we can think about it as a negative power rather than as a quotient and can avoid the quotient rule entirely. Similarly, if the denominator is just a constant, we can use the constant multiple rule to deal with it rather than using the quotient rule. So in example 2 here, we have a function which is a quotient of two functions. It's x to the 6 minus square root of x plus 4x squared all over 2x cubed. However, the best way to differentiate this is not in fact to use the quotient rule, but to simplify first. So the first thing I'm going to do is I'm going to split this up as three separate fractions. We have x to the 6 over 2x cubed. We have square root of x, which is x to the 1/2 over 2x cubed. And we have 4x squared over 2x cubed. Then, x to the 6 divided by x cubed is x to the 3. 1 divided by 2 is 1/2. So we think about this as 1/2 x to the 3. X to the 1/2 divided by 2x cubed is 1/2. X to the 1/2 minus 3 is negative 5 over 2. 4x squared over 2x cubed is 2x to the negative 1. So what we've done is we've actually split this up into three separate fractions and done the division, and we've simplified into something which we can take the derivative of just using the sum, difference, and power rules. So now we want to take f prime of x, and we're going to use the sum, difference, and constant multiple rules to pull these constants out. So we have 1/2 times the derivative of x cubed minus 1/2 times the derivative of x to the negative 5 over 2 plus 2 times the derivative of x to the negative 1. Derivative of x cubed is 3x squared, so this gives you 3 over 2x squared. Bring down the negative 5 over 2. Negative 5 over 2 times 1 over 2 is positive 5 over 4. We have x to the negative 7 over 2 minus 2x to the negative 2. So this derivative was in fact a lot easier to find because we did not use the quotient rule. I'm going to do a couple more examples of situations in which we do use the quotient rule before I go on to talking about higher derivatives. So if we want to take the derivative here of h of x, which is e to the x over sine h of x, we're going to use the quotient rule, do the derivative. H prime of x is going to be the derivative of the top times the bottom minus the derivative of the bottom, which is sine h of x, times the top, which is e to the x, all over sine h of x squared. Derivative of e to the x is just e to the x multiplied by sine h of x. The derivative of sine h of x is cos h of x. Multiply that by e to the x. And sine h of x squared we can rewrite as sine h squared x. For g of t here, this is a little bit more complicated derivative to take because the top of the fraction here is in fact a sum of two separate functions. So we'll need the sum rule as well as the quotient rule. So when we take the derivative, g prime of t, we're going to start by writing out the derivative using the quotient rule. We're going to take the derivative of the top, 1 plus square root of x, times the bottom, which is ln x, minus the derivative of the bottom, which is ln x, times the top, which is 1 plus square root of x, all over the bottom, which is ln of x squared. So when we do this, the derivative of 1 is 0. The derivative square root of x is 1/2 x to the negative 1/2. Multiply this whole thing by ln x. The derivative of ln x is 1 over x. Multiply that by 1 plus square root of x, all over ln of x all squared. When doing higher derivatives using the quotient rule, it's important to simplify after the first derivative before taking the second. In the examples I've done so far, I did not simplify my final answers very much. This is usually because it takes a fair bit of work to simplify final answers and doesn't really give you much benefit. However, in situations where we're going to be taking a second, third, fourth derivative, it's going to be important to simplify. And the reason for this is because if we don't simplify, we're going to end up with a more complicated function, take the derivative of, and we're going to have to use more derivative rules, and we're going to get an even more complicated result. So in example 5 here, I'm going to do the first and second derivatives of the function f of x equals x squared plus 2x minus 2 all over x minus 2. So when I do the first derivative, I take f prime of x. I'm going to use the quotient rule. I'm going to take the derivative of the top, x squared plus 2x minus 2 times the bottom, which is x minus 2, minus the derivative of the bottom, which is x minus 2 prime, times the top, which is x squared plus 2x minus 2, all over the bottom, which is x minus 2 squared. So the derivative of x squared plus 2x minus 2 is 2x plus 2. That's got to be multiplied by x minus 2. The derivative of x minus 2 is just 1. It's multiplied by x squared plus 2x minus 2. And this whole thing is divided by x minus 2 squared. Then I'm going to expand everything on the top, subtract, collect like terms to simplify. If I didn't do this, I would have to use a product rule here when doing the second derivative, and I don't want to have to do that. So expanding this, I get 2x squared plus 2x minus 4x minus 4. Expanding this one, I get minus x squared minus 2x plus 2. Now I'm also going to expand the bottom there. That gives you x squared minus 4x plus 4. Now I can do one more step in simplifying, collecting like terms. 2x squared minus x squared gives you x squared, plus 2x minus 4x minus 2x gives you a minus 4x, minus 4 plus 2 gives you minus 2. It is all over x squared minus 4x plus 4. So now I want to take the second derivative. When I take the second derivative, I'm going to have to do the derivative of the top. So the derivative of x squared minus 4x minus 2 times the bottom, which is x squared minus 4x plus 4, minus the derivative of the bottom, the derivative of x squared minus 4x plus 4, times the top, which is x squared minus 4x minus 2. This whole thing is going to be divided by the bottom, which is x squared minus 4x plus 4 squared. So we take the derivative of x squared minus 4x minus 2, I get 2x minus 4. This is now multiplied by x squared minus 4x plus 4. And now I'm going to subtract. Derivative of x squared minus 4x plus 4 is 2x minus 4. Multiply this by x squared minus 4x minus 2. And this whole thing is divided by x squared minus 4x plus 4 squared. Now here, this is the second derivative. Since I'm not taking a third derivative, I do not need to simplify the second. I could if I wanted to expand the second, collect like terms. It would take a fair bit of work. It wouldn't give me any more information about the second derivative than what I already have here. So I might as well stop here.